So I'm Terrence Barkin, the Executive Director of the Graphene Council, and we're hosting today's webinar on a test project that was conducted using graphene in an asphalt binding system. The testing was conducted at the National Center for Asphalt Technology, or NCAT, which is located at Auburn University and is a leading reference center for additives and formulations for asphalt binders and for asphalt materials. And so we have Raquel Morez from Auburn University and Fan Yin from Auburn University who will be presenting the results. And with that, if you folks would like to introduce yourselves and the rest is yours, we're all ears, and then we'll do Q&A at the end of the presentation. So again, thank you for the work that was done on the testing, and thank you for doing this presentation.
Thank you, Terrence. Good morning, everyone. My name is Raquel Morez. I'm Assistant Research Professor at Auburn University, working at the National Center for Asphalt Technology. I have the pleasure of being working with this study, and I'm going to give now the opportunity for my team member to introduce himself.
Thanks, Raquel. Thanks, Terrence. Good morning, everyone. My name is Fan Yin. I'm an Assistant Director at NCAT. Like Raquel said, we're very excited about the work that we have been doing using graphene in asphalt, and very much look forward to sharing the result with the group today, and look forward to further collaboration on this topic moving forward.
Just for clarification as we go, Terrence said that he's going to open the room later for us to have the questions. I'd like to say that I'll be presenting the data that was collected in the lab, and also when I finalize the presentation, if Fan would like to give more field perspective of what was presented, we'll give him the opportunity to do that. So before starting, I would like just to clarify some of the names that I will be mentioned today in presentation. I would like you to see on this picture, this is a road that you drive on every day, right? So you see here that this is what we call the asphalt pavement. If we zoom in on this asphalt pavement, you would see something like that, where you can clearly see a black component and several rocks. And this is what we have as when we say in the mix design, what is used to build a road. These are the 5 components that are used when we have an asphalt pavement. We have the black component, that is the asphalt binder. We have mineral filler, 2 types of aggregate, fine and coarse, and air. When I'll be mentioned today what was evaluated, I'd like you to understand that we incorporate the graphene to the black component of the asphalt pavement. It's what we call the asphalt binder. So when I mentioned what was evaluated, we included the graphene products into this component here, that is the asphalt binder. The materials evaluated in this study were 1 base binder with a performance grade of 64-22. And we evaluated 4 different graphene products at 3 different dosages, 1, 2, and 3. Here we have an illustration of the products utilized, and we call these additives 1, 2, 3, and 4, so we cannot disclose there is no product name. Here we have the testing plan that was used for phase 1 evaluation. I would like to clarify that the whole goal of phase 1 was for us to be more familiar of how these products work and how can they be worked in the lab. And also, we use a standard Superpave grading system to evaluate the behavior of the product. So we want to initiate our knowledge on the product before moving forward with other steps to perform a more complex evaluation of the additives. But before moving to that, we need to acquire the basic knowledge of how these products work, how we can work with it in the lab, and so forth. So you can see here we have 1 asphalt binder, and for each graphene product, we evaluate 3 different dosages. We evaluate the material when we call unaged, meaning that we have your additive, we blend it with the asphalt binder, and we evaluate properties of that materials without submitting the final blend to any type of oxidative agent. Then we perform 2 types of agent, and I'll be discussing this in details every time that I'll be disclosing the results obtained for each of the testing. We have what we call a short-term agent and a long-term agent. So in synthesis, what we evaluated here was the rheological properties of the asphalt binder modified with the graphene additives. First test that we evaluate was the storage stability test. It's an ASTM standard and is used for us to evaluate the tendency of a polymer to separate from one additive that is incorporated into the binder. Following the storage stability test, we perform a softening test to see the tendency of the specific additive, to be separated from the asphalt binder. So the test is pretty simple. As you can see here on this illustration, it consists of, we have the blend of the asphalt binder with the polymer or the additive, in this case, graphene. We have the materials stored in a cigar tube, that is an aluminum tube, as you can see in this picture. And after condition at cold and room temperatures, we separate the top and the bottom portions of this tube, and we evaluate the properties of the binder on top and bottom. And the property that was mentioned was the softening point, as you can see here in this picture. The softening point, what is it? Is an indication of the fluidity of the binder, meaning is what is the temperature where the binder will start to flow. Why this property is important? Well, imagine that we have a pavement that is to be located in a location that has our environment temperature of 40 Celsius. So we want to have a binder that has a softening point that is higher than 40 Celsius, meaning that that material is not going to be soft at that specific environmental temperature. As you can see here in this table, we use the passing flow and flow limit as indicated in the previous slide of the Georgia Department of Transportation that required that the softening point temperature between the top and bottom portion of the storage stability test cannot be higher than 10 Celsius degrees. As you can see here in this table, for all the additives at the 3 dosages evaluated, none of them give us a difference between top and bottom portions higher than 10 Celsius. All of them, for 2, 3, and 4, all dosages show actually a difference of 0, so no separation. And the only product that showed a higher tendency for separation was additive 1. Then I'm going to now cover what was evaluated in terms of rheological properties of the blend of the asphalt binder with the additives. We use what we call the Superpave Performance Grade system protocol for evaluation of these binders. Basically, the system targets 4 specific properties of behaviors to be analyzed for the materials: production, rutting performance, fatigue cracking, and thermal cracking. And for each of these targets, we have a specific testing protocol, aging protocol, and thresholds that are evaluated to grade a specific asphalt binder. For production temperature or production properties, we use a rotational viscometer at a temperature of 135 Celsius. For evaluation of rutting properties, we use a dynamic shear rheometer, considering the material at the original state and after a short-term aging in an oven. Then we evaluate fatigue cracking, also using a dynamic shear rheometer, but now the material is long-term aged. And then we evaluate thermal cracking, that is the behavior of the properties of the asphalt at lower temperatures, for which we use a bending beam rheometer, and the material is also long-term aged in an oven. And here I will show you the testing apparatus for each one of the properties that was previously described on the previous slide. For rotational viscosity, we use a Brookfield rheometer, and the test is performed in accordance to Ashton T316, where we evaluate the overall handling and pumping properties. This is an important property that we always consider evaluating, especially when we have additives, that because we want to see like how is the workability of the binder after the incorporation of the additives, and if this would change and somehow what is expected as a common behavior in a plant. Then we use the dynamic shear rheometer, Ashton T315, to evaluate both the elastic and viscous properties of the asphalt binders at different times and temperature. Then the bend beam rheometer per Ashton T313 was used to evaluate also the flow properties at low temperatures. And below in the slide, you can see the two protocols for aging that were considered in the study. A rolling film oven per Ashton T240 that simulates the aging that occurs in a hot mix asphalt mixing facility, and the PAV, the pressure aging vessel, per Ashton R28 that simulate the long-term aging of the pavement after that being exposed, let's say, between 7 and 10 years in a road. First results that we have here to present are the viscosity. So that was used with a rotational viscometer. You can see here on black, this is the neat binder, meaning that it was the base binder evaluated in the study without having any graphene on it. And then on the following columns on gray, you can see the binder modified with each graphene product. For all the additives at the 3 evaluated dosage, you can see that the final viscosity was below the specification limit of 3 Pascal per second. So, which is a very positive result. Then we went to evaluate the Superpave Performance Grade of the binders. Just to briefly describe what does it mean, as mentioned when I described the materials utilized in this study, I said that we use a PG64-22 binder. What does it mean? It means that these two specific temperatures are the expected temperatures where that binder will perform well, where the first temperature is the higher temperature to which the pavement could stand, and the second one is the lowest temperature. When we say grade bumping, like when we incorporate additives to the binders, we use a terminology called grade bumping, where we can increase 1 or 2 of these temperatures or both simultaneously to target specific traffic and volume. And generally speaking, if this difference between these two numbers is bigger, better is the performance of the binder. So here on this slide, I have the results of the high temperature performance grade of the asphalt binder, base binder, and the asphalt binder modified with the graphene additives. You can see here that the number that is indicated here on the top of each of the columns is what we call the pass-fail temperature. So it's the maximum temperature that pavement could, that a specific asphalt binder could hold. And you can see here that some of the binders presented lower, a slightly lower pass-fail temperature than the base binder. But as we increased the dosage, that trend was changing. But we did not see a specific decrease on the high temperature of the binders after incorporation of the graphene. So overall, the trend was that after the graphene additives were incorporated to the base binder, in terms of high temperature performance, we saw an improvement in rutting resistance. You can see that, as mentioned in the slide before, for some of the additives, we saw 1 grade bump. Initially, the binder was classified as PG64, but after incorporation of the graphene, the binder ended up being a PG17. For some of the binders, specifically additive 2 at 1% and additive 3 at 1 and 2%, no change in the PG grade of the binder was observed. It remains 64. Then we evaluate the properties at intermediate temperature after the binders were aged in the RTFO and PAV. You can see here on black for the base binder and on blue for the graphene modified binder. At this specific temperature for this testing, what we see is that we wanted this temperature, the pass-fail temperature, to be decreased in terms of improving the properties of the base binder. We can see that all of the graphene modified binders show a pass-fail temperature higher than the base binder, with exception of the graphene additive 3 at 1%. However, the change was not very high, very significant. It means that overall contribution of the additives was not so detrimental. Then we evaluate the low temperature properties of the base binder and the graphene modified binders. The same principle that is used for the high temperature applies to here for the low temperature. We see the pass-fail temperature and the overall effect of the additives on the final PG gradient of the binders. Usually, what we see is that if we increase this pass-fail temperature, meaning that if this temperature becomes more positive, we relate that to a reduced low temperature cracking resistance. So you can see here that some of the additives did increase the pass-fail temperature of the base binder, while some of them decreased slightly, with the difference being not that significant. So you can see that all final PG performance grade remain -22 as the base binder. So the overall conclusion regarding the low temperature PG of the binders was that the addition of graphene had no significant impact on the low temperature cracking resistance of the base binder. Another parameter that we use to evaluate binders at low temperatures is what is called the delta TC, where we use a difference between stiffness and relaxation properties at low temperatures to see the tendency of specific binders to cracking. So you can see here, actually, let me say something else. It is right now, different departments of transportations have different limits for the delta TC as the delta TC threshold. But overall, what we want is delta TC higher or equal to -5C, as being classifying a binder. If the binder is with this range of delta TC, the potential for cracking is decreased. You can see here that overall, the graphene binders decrease the delta TC of the base binder, but that result was not very significant, and none of them got even close to the threshold of -5°C. So indicating that relatively low potential cracking susceptibility. And here we have the summary of everything that was presented in the graph. So what was presented in the graphs is completely included here in this table. As you can see here, on the last column of this table, we have the final PG classification of the modified graphene binders. You see that the base binder initiated at 64 -22. And when we incorporate additive 1, we had an increase on the higher temperature performance grade to 70. The -22 remain. For the additive 2, the 2 higher dosage result in 1 grade bump in comparison to the base binder, jumping the high temperature performance grade to 70. And additive 3, only at 3%, we achieve 1 grade bump. And for additive 4, at the 3 dosage, the 1 grade bump was obtained. And as showed before in the graph for the low temperature performance, we saw that all the binders remain at PG minus 22 as the base binder. Another test that was used to evaluate the graphene-modified binders was the multiple strain creep and recover test that is performed in accordance to ASTM 332 and was conducted in short-term aged asphalt binders, where we can see the creep and recover of the binder. So basically we apply creep and let the binder recover and see its response. We have two outputs from the test: percentage recover to see the elastic contribution, and non-recover creep compliance, JNR. And here we have the summary of the results for the MSCR test for the base binder and the graphene-modified binder. Here we have the JNR, creep compliance, where you can see here for the base binder, we saw JNR of 2.05. And for some of the additives, the majority of them, the results were lower JNR in comparison to the base binder, which indicates that the base binder is slightly stiffer or harder than the base binder, with a section of the additive 2 at 1% that show a slightly higher JNR than the base binder, indicating that the binder is slightly softer. One parameter also that is obtained from the MSCR test is the traffic rating that we call, that is indicated by these letters. You can see here that the base binder and additive 2 at 1% result in a traffic rating of standard, which is for traffic between less than 10 million SL and speed higher than 70 kilometers. And for additive 1 at 2% and additive 4 at 3%, we got a traffic rating of very heavy, where we can use these binders for traffic that is higher than 30 million SL and less than 20 kilometers per hour as traffic speed. And the remaining of the graphene-modified binders were all graded as heavy, being appropriated between 10 and 30 million SL or a speed of 20 to 7 kilometers per hour. So as saw previously, for the high temperature performance grade results, we saw a slightly increasing the rutting resistance of the binders after the incorporation of the graphene. And then the other parameter that was used, that is obtained from the MSCR, is the percentage recover. So you can see here, and as expected, we are not incorporating any elastic component for the graphene in terms of polymeric contribution. So we are not expecting that the graphene would significantly increase the elasticity of the binder. And you can see by these results. We can see that for the additive 1, we saw a slightly higher percentage recovery in comparison to the base binder, as well for additive 4. But this is related to the fact that, as indicated on this previous slide, this specific binder were harder in terms of JNR than the base binder. And lastly, the last parameter that we used to evaluate, it was the global roll parameter, that is this GR here. This parameter is obtained from dynamic shear rheometer master curves, where the binder is tested at several temperatures and several frequencies. And we use this specific parameter to see the ductility and block cracking resistance of the binders. What has been seen and has been proved by field data is that when the binder starts to get aged or more oxidized, we see an increase on the global roll parameter. Therefore, increase on the cracking potential cracking susceptibility of the binders. On this slide, we have the global roll parameter plot in a black space diagram, where we have complex modules of stiffness in the y-axis and phase angle, that is the measurement of the elastic response on the y-axis. And we have these bold and dashed lines on this graph indicating the limits, where the bold one is a limit where if a binder, neat binder, exceed that bold line, means that it has should already been showing visible cracking in the field. And if it's between these two lines, mean that is the cracking is initiating, beginning to propagate. And if the binders are located below the dashed line, mean that we are good, no potential for cracking. We have to say that these thresholds, they were defining field experiments for unmodified asphalt binders. So meaning that the applicability of these limits for binders that are modified with any type of additives, it needs to be validated. But what we can see is that for all of the binders, before and after long-term aging, for the base binder and for the binder modified with the graphene additives at all the evaluated dosages, we did not see any of the binders in the cracking damage. So none of the binders show potential for cracking. By utilizing also the Glover-Rowe parameter, an aging index was calculated, considering the Glover-Rowe after short and long term, and the Glover-Rowe of the original material before being subjected to any type of age. And here we have the Glover-Rowe aging index of the base binder on black and on blue for the graphene-modified binders. Usually, if the aging index is lower than the control, than this black column, mean that the tendency of these blends of binder with additive for cracking or for aging or the aging rate of these additives are being lower than the base binder. So overall, what we can see here by these results is that the 4 evaluated additives at the 3 dosage for each one apparently reduce the binder susceptibility to aging. And the aging protocol used for evaluation here, as indicated in the beginning of the presentation, was the standard aging procedure that is used for grading or quality assurance of the base binder. 20 hours of PFE aging that simulates between 7 and 10 years of the pavement being in the field. And here we have the overall Glover-Rowe parameters and complex modules, meaning stiffness, and phase angle, meaning elastic response of all the binders. And this is what was plotted in this graph showed right here. So overall, from what was presented today, we saw that for all the additives evaluating this study, up to 3% of graphene was positive. No issue was observed for regarding storage stability, meaning that none of the additives at the dosage up to 3% show tendency for polymer separation, meaning that, for example, if this blend of binders were stored in a tank, we wouldn't have separation between the graphene and the binder. For the only one that showed a limit of between 10 Celsius degree between top and bottom portions after the storage stability test was additive 1, where we saw that for that specific additive, the maximum percentage that could be used for this specific binder would be 2.5%. We saw that for all the additives at dosage up to 3%, we saw no negative effect on the viscosity, where all the blends show viscosity results at 135 Celsius degree, way below the limit of 3 Pascal per second. We saw improved rutting resistance, indicating that we ended up simple words, with material being harder or stiffer than the base binder for additive 1 at all doses, additive 2 at dosage at 2 and 3%, and additive 3 at dosage of 3%, and additive 4 for all dosage. We saw that in terms of improving fatigue resistance that occurs at intermediate temperatures, only one additive showed a pass and fail temperature lower than the base binder, that was additive 3 at 1%. However, the pass fail temperature that was resultant from the binders modified with the graphene products were not significantly higher than the base binder. We did not see a detrimental effect for any of the additives at the 3 doses evaluated in terms of cracking resistance and low temperature. And when considering the Glover-Rowe parameter results after 20 hours of PAV aging, we saw that the graphene products improved the aging resistance of the base binder. With that in mind, and as it was indicated in the beginning of the presentation, the results for us were very positive in the sense that, first, from the literature, we saw that before performing this specific study, we did a literature review to understand a little more of the material. And what we are able to see on the literature is that the dosage used for the graphene products were generally very low. Of course, that was product dependent and depends on the size of the graphene utilized and so forth. But what we saw is that the dosage were often very low because of the tendency of segregation of the graphene. So we got positive results in terms of seeing that we could go to up to 3% for basic classification of binder. We also saw positive results in terms of how could we work with these materials in a lab, if it's for any department of transportation to accept or not, or to get interest on working of this type of products. The basic properties of these materials needs to be known, and that was achieved on phase 1. Another positive aspect is like we did not have knowledge on how we could work with these products in the lab. So, and what we found is that it was very easy. The material are very blendable. We had no issues with preparing the modified asphalt binders. We did not need specific equipment or higher temperature or adjustments in our routine protocol to modify the binder with the graphene additives. So overall, the phase 1 objectives were very positive for us. But again, it was a basic evaluation of these additives effect in base binder for us to start to acquire knowledge of how these materials behave. So further evaluation is what is proposed as a following step for phase 2. If you remember from the last set of data that was presented, we saw that these additives, they decrease the aging susceptibility of the binder. However, we would like to really quantify if these additives could really decrease this aging susceptibility when they are subjected to a very long-term aging. Because when we age the binder for a longer term than what is used in the Superpave standard protocol, we can clearly capture the effects of aging on the binder in terms of, for example, increased stiffness or increased hardening brittleness for the binder. So with that in mind, we would like to see how these blends goes or perform in terms of rheological properties after they are subjected for 40 hours and 60 hours of PAV aging with the additives. And after these additives were being aged in these 2 extreme aging protocols, we would measure the rheological properties of the binders in terms of performance grading, exactly what was mentioned today. What would be the effect after long-term aging of the specific additives when considering low temperature cracking, for example, and also at intermediate to cracking, incorporating more advanced testing protocols than what's presented today. So this is what we are targeting with phase 2 evaluation. Another thing that is we would be looking for is like in terms of the chemistry of the binder, how are these materials affecting, or if they are or they are not interacting within the binder. So for that, we would use Fourier transform infrared spectroscopy to evaluate functional groups that could be resultant or could be modified or affected by the incorporation of the graphene additives. So with that in mind, and from the results that we obtained from phase 2, we saw that we could go up to 3%, right, from the results from phase 1. So we estimated using 2 dosage on phase 2 for further evaluation to see also like if in a higher dosage or in a lower dosage, when considered long-term aging, the agglomeration property or segregation property of these products could be captured. And with that, I finish my slides today, and I'll now give the opportunity to Fan to give his input on our results.
Thank you very much, Akil. I think you did a great job summarizing the test results that we have collected so far. I guess the only thing I would add at this point is kind of like, tie back to the concluding slide that you showed earlier, saying like, based on these preliminary results, we saw the improvement in rutting resistance and also improvement on the aging resistance. This is something that we have discussion with Terrence before. Right now, I mean, at least in the United States, the primary distress in asphalt pavements is cracking, okay? And, if we go back to the history of, about 25 years ago, our industry was struggling with rutting, which is the deformation distress. But now we don't have rutting issues, okay? We are having cracking issues, which have lots to do with, the quality of the asphalt binder, aging plays a significant role. So the reason I want to mention that is like, if we want to kind of like further, expand, the path of looking into the use of graphene in asphalt, I think we need to more focus on the cracking side, because that is a problem the industry is facing. I mean, that's something that's going to be more of interest to state DOTs or to like non-state highway agencies. They will ask us, if I use this material, how will that help us with the cracking performance? And I think, based on these phase 1 results, the improved aging resistance is very promising. Like we said, aging has a lot to do with cracking. So that's why, like the next phase, we strategically, scope the work to focus on the aging benefits. If this is something that can really work out, then it has the potential to improve the cracking performance. And that's something the asphalt industry really want to pursue. If we're only focused on rutting, it's a good thing, but we don't have the problem at this point. So that might be a little bit tricky to deal with. But like I said, I 100% agree with what you said. The phase 1 results are promising, but also we want the folks on the call to keep in mind this is a preliminary, almost like a proof of concept study. At this point, I think the phase 2 will be very interesting to further investigate the aging resistance side and see how the results turn out. So,
excellent. Well, thank you both for the presentation. We have quite a few questions, and Raquel, if you don't mind, maybe we'll just stop sharing, because a lot of the questions I don't think we have to refer back to the slides to answer the questions. But let me kind of go through some of the questions that we had. There's quite a few, so which is excellent. So there have been a couple of questions about what was the graphene that was used in the study. So we had 4 different samples here, and for not everybody on this call is going to be familiar with graphene. So graphene does come in many different types and forms. Graphene nanoplatelets, graphene oxide, which has been oxygen added to it, which is on the surface or the sides of the actual particles. And these are nanoscale materials as well. So in the study that we had with the 4 different samples, we had graphene oxide, we had a modified graphene oxide, we had a graphene nanoplatelet, different types of material. And I think that's very important to understand because the 4 materials did perform fairly similar to one another. We didn't see huge deltas that one performed really well and one performed poorly. So that's just the question on the graphenes that was used. And then Raquel, you made a comment about the dispersing and adding the graphene to the materials and that was easy to do, which in many cases working with graphene, it's the opposite, that dealing with this nanomaterial and dispersing in a host resin system, for example, is quite difficult. Can you just say what was the method that was used to disperse into it, and what evidence do you have that it was evenly dispersed or, throughout the matrix?
So we use the standard protocol that we do for additive incorporation in the lab. We use a low shear blend. So for some polymers, I'll give an example. If we use a SPS polymer, for example, where we need to break the pellets of the polymer to try it to disperse in the asphalt binder, the first step that we do in the lab is to use a high shear blend, and then we can move back to a low shear blend. For the graphene incorporation of the binder, for example, we only use the low shear blend. So the asphalt binder is heated, let's say, between 135 and 150 Celsius to make sure that the material is pretty fluidable. Then it's incorporated in a low shear blend, and we did the measurements by weight to achieve a specific dosage of graphene of 1, 2, and 3%. We only just include the graphene inside the blend and use a low shear blending for 30 to 45 minutes. Regarding the questions like how can we assure that the graphene is dispersed? What was used here was the first results that was said is that I'm not evaluating dispersion specific in terms of the morphology that is modified or not of the binder after incorporation of the graphenes. Morphological evaluation we did not perform. What we did was another way of indicating if the material was dispersed or not in the binder was the storage stability test to see if the material is well dispersed in the binder, we assume that we don't have difference between the samples that are located between the top and the bottom of the storage stability cigar tube after the material is subjected for low temperature and low temperature for up to 6 hours of storage. So that is the way that we use in this study to evaluate if the material was or not dispersed in the binder. And as you can see by the results, it was exactly for most of the additives, the same value obtained on top and bottom, meaning that we saw no difference of graphene being agglomerated in the top or in the bottom of the binder.
Thank you for that. Thank you. There are quite a few questions related to chemistry and a little further analysis. And for example, contact angle with water, rain on the surface and these kind of attributes. These are not attributes that we tested, and we don't foresee doing that kind of testing going forward. I think what's been proposed for the next phase, phase 2, is to extend and do similar testing so that we can compare the results for an extended aging period. But one of the questions, and if you guys don't mind, I'll handle it simply because we have experience with this, was what is the potential for release of graphene from the asphalt binder? Now, we've done a lot of work with graphene in other polymers, for example, into fabrics, into coatings, into composite resin systems. And as a nanomaterial, once it gets embedded into a host material, not only is it difficult, it's virtually impossible to release the graphene from the host material. It just doesn't liberate, even with abrasion. What will end up happening is you may have a particle. In this case, it would be a particle of asphalt that has graphene in it, but the graphene will not separate from and become a free particle or a free agent. So I know that people are always worried about this, or they're asking, can the graphene become freed from that? It's a relatively small percentage. It's fully encapsulated in a host material. And when we test materials that contain graphene, we actually have to dissolve the host material with a strong acid or some other agent in order to liberate the graphene. It's that difficult. So I just wanted to address that particular question. I'm
It
just
has one question. It has one question here, Terrence, that I would like to answer, please. That I should have said in the beginning. So it has a question. It says, why additive 1 was added at 2.5%, while others were at 3%? So for that specific additive, and this is the additive where we saw the highest difference between top and bottom from the storage stability test. That specific additive, we did the blend at 3% graphene. And when the sample was left for the rheological evaluation on the dynamic shear rheometer, the frequency sweep test that is used to calculate the overall parameter is a long test. It takes up to 6 hours for the binder to be evaluated at different temperatures and different frequencies. For that specific additive at 3%, what we observed was like, while the test was running overnight, the material solidified. It became like a rock. So it couldn't be tested. That's why we said, okay, 3% is too much. How much could we incorporate of graphene to be able to test? And that's why we found 2.5%.
Thank you. Thank you for sharing that. One of the questions here is, how did these graphene enhanced binder results compare with other type of additives, maybe that you have measured, with polymers or SBS or, some other additives? Do you have a comment on that?
That's a great question. It's something that we discussed before, right? So when we try to modify the asphalt binder and specific additives, we usually target a specific benefit of incorporating some of the additives. For example, when we incorporate SBS, we wanted to see improvement in the elastic response. That is beneficial for a lot of properties when the road is placed in the field. And another thing also, depending on the polymer, we also see reduction on the aging susceptibility of the overall binder. Regarding the specific of graphene, we did not compare in this study any of these binders with a specific additive. But what we would like to say is that we saw that this has a potential of decreasing aging. And in terms of comparing specifically to performance of other additive, I would rather to have data collected before we just answer and say like we think that it behaves equal or different, because I think we still have to look into that. However, as indicated, the results were positive in the sense that we did not have any issue, and we saw positive results considering a higher dosage of 3% for the materials. And if Fan would like to add something, I will let him.
Yeah, I agree with what you said, Hakil. I think the only thing I would add is that just kind of like for the benefit of the discussion is that our industry, asphalt industry, we have a long history of using asphalt additives for paving applications. But I would say like those additives are intended for different purposes. Like you said, like some of those additives are really added to enhance performance. SBS is probably the most successful one, and that's most commonly used because it helps a lot in terms of the performance, no matter we look at the rutting, the fatigue, or the aging resistance. But also there are some additives that have been added in the asphalt for other reasons besides performance. It could be sustainability, it could be some others. So I guess the reason I want to mention that is like sometimes like when we compare like additive A versus B versus C, if they fall under different categories, and it may not be an apple-to-apple comparison. I hope that makes sense. And like Akil said, we are excited about these phase 1 results because of the aging benefits. Okay, and that might be kind of like the unique perspective that we can get out from these potential application. So I guess just want to echo what Akil said and just add a little bit context to the discussion. So.
Well, one of the reasons we did this study, now speaking from the graphene sector perspective, is we wanted to have trusted empirical evidence and data using the Superpave testing protocol, which is respected by the DOTs in the United States, and I think translates to other departments of transportation, because we have folks from other countries on this call. What I would encourage is we would like companies to participate in moving forward with phase 2 for the longer term aging attributes of this material. The other observation I want to make is that there were no negative trade-offs from using graphene. It wasn't that you had an elevation in one performance metric and there was a compensating decrease in another performance metric. And I also took note of the fact that, you know, the traffic ratings for this improved binder were elevated. It improved the aging aspects. And so we do want to go forward. Now, if anybody wants information more, because some folks are asking about the type of graphene used and that sort of information, you know, the Graphene Council is here as an independent, neutral representative of the sector. We can put you in touch with graphene companies. We can answer questions that you might have specifically about the materials that were used. I do think that we would go to phase 2 testing project to test these physical attributes. And then some of the questions that are here regarding the chemical analysis would be, once we've arrived at a point where we see graphene has a significant beneficial role to play in this, then we can do further analysis on, you know, the more detailed chemical analysis and see how it interacts within the systems. Does that make sense to both of you, that approach?
Yeah, it does.
Okay. One of the questions, you know, was all the graphene and all the sets the same size and layering? No, it wasn't the same material, but it was all graphene. And according to the ISO international standards of graphene, it's 10 carbon layers of sp2 bonded carbon or less. The Graphene Council, we also write the standards. We do testing for materials. And so we know the material that was used in this test. And by the way, this was a blinded study. We knew the materials. We knew who was supplying the materials. These were then forwarded to Auburn University for the incorporation into the testing. And that's why you see the results as sample 1, 2, 3, and 4. I don't have any additional questions. I think at this point, we've covered quite a lot in the presentation. But do you all have see any of the questions from the audience that you would like to address that maybe we haven't talked about yet?
Well, I'll start one. Akil is looking at some of the questions still in the chat box. I saw one talking about the different production method of graphene. I think that's something definitely falls better under, I mean, you guys will have, so since you know graphene much better than we do. I think as Akil mentioned, and Terrence, you also pointed out, in the phase 1 study, when we look at the 4 products, which are different, and we did not see, like, you know, those 4 products have significant different results on the binder applications. But, you know, how much further we can, you know, extend that conclusion, I think that's still yet to be understood. You know, that's something that we deal with lots of, you know, other additives that has been used in asphalt. You know, recycled plastic is one. You know, I'm sure like some of you have heard about those discussions are using recycled plastic in asphalt. And then there's a lot of questions about, you know, how can we standardize, you know, the properties of those, you know, recycled plastics for paving application. And I think the same question will be asked by, you know, the state DOTs moving forward, you know, about the graphene. I mean, that's something that's, you know, not something we need to deal with right now, but I just guess want to put that on the table so that we can keep in the back of the mind as we move forward, as we continue to get positive results, then we need to think about those. You know, at the end of the day, you know, DOTs, the state highway agencies, they need to specify those material to be able to use in asphalt. And, you know, what are those, you know, specifications about this material that are important? That's something that's, you know, that will require like you guys and, you know, the asphalt community to work together to tackle that. So.
Excellent. Well, on the regulatory side, graphene within Europe has been approved under the REACH regulations up to, I believe it's 10 metric tons per annum capacity per producer. And in the United States, the Graphene Council is working with EPA under TSCA registration for graphene as a material. There are forms of graphene already approved under TSCA. We have a very complicated system with EPA in the US, and that each company comes with its own material to get its individual approvals. But the other thing from a practical perspective, graphene capacity for production is over 23,000 metric tons per annum. There is commercial availability of this product. So, it's one thing to test something in a lab and see if it works. It also needs to be able to be supplied on a commercial scale, especially for a large volume product like asphalt or bitumen binder. And that, again, is kind of the interface where the Graphene Council plays, that we work with commercial producers of this, as well as working with excellent institutes like Auburn University to do the scientific testing to get the data we need to know if it works. And to be very concise about this, the question we had at the beginning of the study was simple. Does graphene have a beneficial effect on asphalt binder system, yay or nay? And what we find is that it was positive or at worst neutral across the critical attributes of an asphalt binder, in that you had an increase in the performance grade rating on the upper end, and you had these other positive attributes. And not to lose sight of this from a commercial applicability point of view, as Raquel said, it was easy to handle in terms of dispersing in the host material and not needing additional equipment, not needing, you're already using additives in many cases. So you're not requiring some special process, et cetera. So it's basically a drop-in solution. I think all that is extremely positive. What I would like to do personally is to hear from DOTs and from other folks in the field to understand what is the value of this improved aging attribute, and their interest in our second phase study, and for graphene companies to participate in the second phase study as well. Any company that wants to put their material either through the phase 1, phase 2, or both can add to this so that you get the performance data for your particular material. And we encourage you to do that, and that would be done through the Graphene Council, since we're organizing and managing the study from the project perspective. So with that, I want to say thank you again for all the work that's been done, for the detail, the thoroughness of the testing protocols that were run, and appreciate working with you guys, and for taking the time to participate. Is there any closing comment you all would like to make before we conclude today's webinar?
Just say thank you for the opportunity. It was a pleasure work with you all, and to start to get knowledge on this product. Looking forward for the next step so we can start to understand better how it works.
So, fun?
Yeah, absolutely. I agree. Like, it has been a fun journey working with this material, and appreciate you guys' interest and look forward to the next steps. So.
All right. Well, thank you, and thank you to everyone. We will distribute copies of the slides as well as a link to the recording so that you can refer back to it. And if you have additional questions or just general information about anything related to graphene, that's what we're here for. Please reach out to us. Thank you all. Have a great rest of your day. Thank you.
Okay. All right. Thanks, everyone. Bye.
For more information and to connect with expert partners, contact the Graphene Council at thegrathenecouncil.org.